Hi, my name is Scott Simpson, and today we're going to be talking about quantum numbers. So there are 4 quantum numbers, and what we're going to talk about is how to determine those values and what they mean. So there are the 4 quantum numbers. They come from quantum mechanics, which you may learn in physical chemistry if you continue later on with your chemistry education. If not, this is just a clear and quick way on how to determine these and what they actually mean. They're related to atomic orbitals, which we're going to talk more about in a little bit. So, since there are 4 quantum numbers, we should probably talk about what each one of these are. So, the first quantum number is known as the principal quantum number. It is n. And n takes on whole discrete integer values, so integers. So values starting from 1 and going to, I don't know, infinity. Yeah, you have infinity, right? There we go. Next, we have L, which is known as the angular quantum number. And L takes on values of n minus 1, so the principal quantum number minus 1. To 0. We'll talk more about what that means in a little bit. Next, we have the magnetic quantum number, ML. So M sub L. And this can take on values from negative L to positive L, which includes everything in between. Next, we have the simplest quantum number, MS, which is the spin quantum number. And this can take on values of either plus 1/2 or minus 1/2. And this is for the spin of the electron. So let's get into what these numbers actually mean. Or let's first go through an example that's common of Gen Chem tests when they try and quiz you. So normally in Gen Chem what they like to do is they like to list a set of quantum numbers and have you try and determine which is correct and which is incorrect. So let's do that for 3 cases. So we'll call this one case 1, case 2, and case 3. And what I'm going to do for you is we're going to step through and determine if each one of these is correct or incorrect. So let me finish writing this out. And MS is just the same. Alright, so in case 1, we have a principal quantum number of n is equal to 1. This is possible. The quantum number can take the principal quantum number can take any number from n to infinity. Next, we have L, our angular quantum number. This value is 1 in this case, which is incorrect because L can only take on values of n minus 1 to 0. In this case, this is the same value as n. So this line is incorrect because of L. So incorrect. Next, we have ml is equal to 0. This would be fine, except we have determined our L is incorrect, and our ms is minus 1/2, which is also correct. But this whole line is incorrect because our L value is not an acceptable value. Next, for our second case, we have a principal quantum number of 2, which is fine, and L equal to 0. Now I said our angular quantum number, L, can take on values of n minus 1 to 0. This is 0, so it should be fine. Next, we have an ml of 0. Now ml, like I previously stated, can take on values of negative L to positive L. So, since our L is just 0, we can also take our ml to be 0, which is correct. And we have an ms of plus 1/2, which is also correct. So, this is fine. So we're okay with our second example. Now our third example, we have a principal quantum number of n is equal to 3, which is okay. We have an L value that is smaller than n minus 1, so that's okay. We have an ml value of negative 1. Now is this fine? I did say previously that L can take on ml can take on values of negative L to positive L. In this case, it's negative L, so our ml is correct. And our ms is just a positive 1/2, so we're fine here. So this one's okay too. So that's how you spot out if you have a correct or incorrect list of quantum numbers. Next, let's talk about what each of these quantum numbers actually means. And how they relate to atomic orbitals. So, we have our n value, which is known as our subshell value, or our shell value. So for example, hydrogen would have an n value equal to 1. Next, our L value can also be known as our subshell. What I mean by this is if we have an L equal to 0, we're talking about the s orbital. If we have L is equal to 1, then we're talking about one of the p orbitals. And then if we have an L equal to 2, we're talking about the d orbitals. Next, what does our ml value actually mean? Well, our ml value is talking about the specific orbital that we're talking about. So, if we have an ml value equal to 0, that means we have an L value that's also equal to 0, which means we're talking about the s orbital. The s orbital only has one orbital, right? So, that's why we only have one value of ml for L is equal to 0. But what about if we switch to L is equal to 1? Well, if our ml value is equal to 1, that means we can have, or excuse me, if our L value is equal to 1, that means we can have an ml value of positive 1, 0, and negative 1. And if you notice, you should know that we have 3 p orbitals. So the px, the py, and the pz. So let's call this one right here. Then we have one that extends up. And then we have one that sort of comes out of the board, but I'm going to draw it kind of funny like that. So we have 3 p orbitals, right? Now, this makes sense. If we have an L value that's equal to 1, we know we have 3 p orbitals, right? And each one of these orbitals can accommodate 2 electrons. So it ends up working out with their quantum numbers. So what I've hopefully demonstrated to you today is how to spot faulty quantum numbers, what the quantum numbers actually mean, and how to determine the values of them. Thank you very much. What's happening?